Today we will continue with the lead compensator, and as I mentioned yesterday, we will do this example taken from the passé question. This was asked in last year in the final exam last year, 2019-2020. I hope that you have done it. Let's do again together. It's mentioned here, a control system is given by the following open loop transfer function. When the static at a constant kV20, the dot plot is given in figure. This is the one, magnitude and also the phase of the system. Here, K is not mentioned. As we know, in order to have a dot plot, we need a value of K. K is not mentioned here, but we will know the value of K by solving KV equal to 20. It is mentioned that it is plotted with KV equal to 20. We can also confirm KV equal to 20 by looking into the magnitude. We know that if we make a straight line, until it crosses 0 dB, it will touch 20. 20 is here. This is 10, here 20. The graph here is, I'm not sure, is slightly shifted. When I printed, it is okay, 20. If I make it cross, it will be crossing 20. Okay, this one we need to check. On my, when I printed, it is okay. Oh, sorry, 20 is here. Yeah. 0 dB is here. 20 here. Sorry. It is okay. 20. So we know that if we make a line from here, a straight line, it should touch 20 like this. This is KV 20. Okay. Right. Design a lead compensator for the system. These are the requirements. The phase margin is 50 degrees. Again, here it is given directly 50 degree. Sometimes, as I mentioned, it is described by a phase margin, damping ratio, and also sometimes by the overshoot. Here it is phase margin 50 degree. And here there is another requirement, gain margin, at least 10 dB. Actually, gain margin is not designed by lead compensator, but perhaps here, if we improve by using lead compensator, the gain margin can also be obtained by 10 dB. But again, lead compensator, we will only design based on the phase margin. Let's start by looking into KV so that we know the value of K. KV is limit S to 0 SGS. We solve the formula, we get 4K 2 over 2 equal to 20. Then we can solve for K. K is 40 over 4, 10. Therefore, the dot plot in the figure is plotted using K equal to 10. Although it is not mentioned, but we know it is plotted with K equal to 10, so that we get KV equal to 20. Right, that is the first one. Let's move. Our desired phase margin equal to 50 from the requirement, from the design requirement. Now we need to know the original phase margin. The original phase margin can be obtained from the root locus given. From the dot plot given. I will phase margin is obtained when the magnitude cross 0 dB. Cross 0 dB here is about 1, 2, 3, 4, 5, 6. But 6 point something, maybe 6.2. Okay. This is let's say 6.2. 6.2 is the omega equal to 6.2 radian per second is the gain crossover frequency. Right, when it cross 0 dB. So that is the 6.2 radian per second. Now we look into 6.2. 1, 2, 3, 4, 5, 6. 6.2 about here. So maybe 100 and 120. Maybe 100, about 120, 162 or 63. Let's say 1 minus 162 degrees. I think maybe 163. Okay, it is just close. So this is the phase margin, the difference between the phase and 180 degrees. Phase margin. So phase margin is 180 minus 162 degree equal to 18 degrees. Phase margin. Original system. Right? Please look into your dot plot. Maybe you get different value, slightly different value. It is okay. So original phase margin is 18 degrees. Therefore, the phase required from the lead compensator is equal to, we want 50 degrees. Originally, it is 18 degrees, but we have to add 10 degrees a correction factor. Although not mentioned in the question, we can add 10 degrees. It is a norm to add 10 degrees. But it is not wrong also if you did not add a correction factor. Not a correction. So 10 here is a correction factor. So 50, 60, 42 degrees. So we want 42 degrees from the lead compensator. Now we start to design. Okay, although I just put number 1, although many previous step here we need to also obtain. Number 1, as we did yesterday, we apply equation 2. Equation 2 is phi max equal to sine inverse 1 minus beta 1 plus beta. 42 here will be considered as the phi max. We want to add 42 degrees into the system. So sine inverse 1 minus beta 1 plus beta equal to 42 degrees. 1 minus beta 1 plus beta equal to sine 42 degrees. I have checked 42 is 0.6691. 0.6691. Right? If you solve, you get beta equal to 0.1982. You can solve again here. You can redo. Again, you need to redo this one. I just skip calculating here. Beta 0.1982. Once we get beta, then we apply another equation. Apply equation 3. Equation 3 is the maximum, the gain at the maximum, at omega maximum, frequency maximum. So G, C, J, omega max. The magnitude is 1 over square root beta. This is the magnitude when omega maximum. We apply substituting the value 1 over square root 0.1982. If you solve, it is 2.246. Right? But we want in dB because we are dealing in dot plot with dB. So next, we also want in dB, CJ omega max. In dB is 20 log the value 2.246. 2.246. It is 7.03 dB. That is the second step, finding the magnitude when omega max. Okay, this is the place, omega max is the place in which we will add the 42 degrees, phi max. So in order for the phase margin to be obtained, we need to make sure at omega max that magnitude cross 0 dB. So how to do it? We need to find a frequency in which the magnitude equal to minus 7.03 dB. Because if we add minus, when we add 7.03, together with minus Z7.03, then we will confirm, we can ensure that it will cross 0 dB. Therefore, we will look into the magnitude here and find minus 7.03 dB. 2, 4, 6, 7 here, minus 7 here, minus 7 dB. We look into this. It's about here. Maybe here. This is minus 7 dB. And if we look into it, this is about between 9 to 10 radian per second. So perhaps we can take omega here is 9.5 in between. You check on your own. Perhaps you get 9, perhaps you get 10, but maybe no, should be between 10 and 9 and 10. Let's take 9.5. This is called omega max. Omega, when the magnitude is minus 7.03, in actual should be it should be minus 7.03. Of course, we were not able to get 0.03, so minus 7 also of course not so accurate. Let's take omega max 9.5 radian per second is obtained here. Right? So from the graph, from the dot plot, omega max is 9.5 radian per second. That is step number 3. Let's move to another step. The next step, once we get omega max, we can apply the last equation. Apply equation 1. Equation 1 say that omega max is equal to 1 over t square root beta. And we know omega max, 9.5. Then we can get, we can calculate for t. T equal to 1 over 9.5 square root beta. Beta, our beta 0.1982. 0.1982. If you solve, it is 0.2364. Right? We already have beta. We already have t. Then we can write the transfer function. The transfer function for lead is 1 over beta s plus 1 over t s plus 1 over beta t. This is the one we write this. We wrote this yesterday. Then we can, of course, substitute those value. 1982 s plus 1 over t. T is 0.364 divided by s plus 1 over beta 3.982 and t 2364. Okay, we can further calculate. solving, if we can simplify the transfer function, it will be 5.0454 S plus 4.2301 over S plus 2031.3426. So this is the transfer function of the lead compensator. And the equation, the question asks you to design and to obtain until the lead compensator transfer function. This is the answer. But sometimes we also will be asked to obtain the overall transfer function. That means with the original system together with the lead compensator. And the overall transfer function normally is the open loop transfer function. So the transfer function is G original system multiplied with G lead compensator. Okay, because we will do like this in the block diagram. This is G lead, and this is G, the original system. So the overall transfer function meaning this. We multiply these two, G lead and GS. Then if we multiply, originally GS is here, this is GS, 4K SS plus 2, we know K equal to 10. So 4, 10, S plus 2, multiply with GC. GC is the GC. Right, I've calculated it. It is, you can multiply 40, multiply with 5, you get 201.816. So S plus 4.2301, S plus 2, S plus 21.3426. This is the overall transfer function of the system when we add the lead compensator. Any question before we move on? Any question during the design of the lead compensator? Please ask if you have any question. Is it understood?
Yes, sir. Understand.
Okay, good. We'll look back into the question. I mentioned just now, the question somehow give another requirement, the gain margin. Okay. Normally, gain margin is not in the requirement when we design lead compensator. You can see that we designed the lead compensator here only by using the phase margin requirement, 50 degree. Okay. Gain margin, we can only show whether it can be obtained or not. Okay. If we use MATLAB, then easier. we design lead compensator, then we see we check for gain margin, whether it can be obtained or not. If not, then we have to maybe slightly modify the lead compensator. But in the exam, whether as we do not have the MATLAB during exam, what we can do, we can only sketch. We have to sketch. We have to sketch the this one, the compensated system. This is compensated system. We have the original system, and then we have to sketch the lead compensator, then we can add. That is the only way to know the gain margin of the system. Okay. We need to ensure, that is number 6, just for this question, because they add gain margin. We need to ensure that the gain margin of 10 dB is obtained. Somehow, in this for this question, I will show later. I will show after this. Okay. You can see here the system, original system has G S is 40 S S plus 2. The original system has 2 poles here. 2 poles, meaning that one pole gives 90 degrees, the other pole gives 90 degrees. That's why you can see the phase here, maximum go to 180 degrees. It will not cross 180 degrees. If we have a system like this is just for information. 180 degrees. This is 0 dB, magnitude and phase. If the magnitude is like this, if the phase is like this, if the phase did not cross 180 degrees, I will redraw it. Okay. So normally when we want to find gain margin, we see when it crosses 180 degrees, then we calculate, we see the gain, the magnitude at that point. But when no 180 degrees crossing, like this, that means gain margin is infinity. If you see system like this, in which it did not cross 180 degrees, the gain margin is very big, infinity, and the system is always stable. Okay? Because usually gain margin is this. This is gain margin. But when did not cross 180 degrees, then gain margin is infinity. Similar to this system, because the system only has 2 poles and it did not cross 180 degrees, so the system is the original gain margin is infinity. Okay, when we add lead compensator, lead compensator also has one pole. So it will be 90. So we have 90 degrees here, 90 degrees, and 90 degrees. 270 degrees. It will cross. But lead compensator also has 110. Here also 90 degrees. So in total, because they have 3 pole, 1 0, it will also not cross 180 degrees. The phase of the compensated system does not cross minus 180 degrees. So again, the gain margin is always infinity for this system. Also for the compensated system. And that ensure gain margin more than 10 dB. So the question here, given that one so that you understand, it will not cross 180 degrees, then always gain margin always can be maintained for more than 10 dB. Right? Okay, I plotted using MATLAB the effect of adding lead compensator. Okay, the blue one is the original system with K equal to 10. Okay, here also K equal to 10. The original system. When we add lead compensator, GC, the one that we obtained just now, with this, it is the red color. The red color is the compensated system. Now let's see when it cross 0 dB. It cross 0 dB here. The one that I can get is 9.26. 9.26. We designed for what 9.5 just now, radian per second. This is not so accurate. 9.26. And if we check at that point, we get phase 126 degree. 126 degree. If we check the phase margin, it is 54 degrees. Okay? We want 50 degrees. So it's about this. It's about the one that we obtained. Again, the value that I obtained is not that accurate here. So that means we can achieve our desired phase margin about 50 degree. And again, another important point, we can see 180 degrees. The phase did not cross 180 degrees. So the gain margin is always infinity. Okay, so then therefore we have successfully designed the lead compensator and achieved both gain margin more than 10 dB and phase margin of 50 degree. All right, any question on lead compensator? We start from here. You need to understand because as I mentioned, lead and lag will normally come out in the final exam. So you have to do it. You can see, I think lead is easier than lag compensator. Lag you need to draw on the board plot, although not that difficult. If you follow the step, it should be okay. But lead only you read from the board plot, read some data from the board plot. Right? Finally, as we have PI, we have PD in the time domain, we can combine PI and PD become PID. In frequency domain, we can also combine lead and lag compensator in order to improve both transient and also steady state error. Remember, we use lag to improve steady state error. We use lead to improve the transient response. We can together add in order to obtain both. Okay, and this is the way to do. We will improve the performance at low frequency range using lag compensator and improve at high frequency using lead compensator. Okay, but in the syllabus, we will not do both. It is quite complicated to do both manually. That need to be done perhaps using MATLAB, could be easier. Okay, that complete the syllabus of SKEE3143 control system design, in which we have 3 chapters. The first one is root lockers. Second one, we design PID using root lockers and also using PID tuning. And the last chapter is related to frequency response, in which we started with sketching board plot and then designing lead and lag compensators. Any question before we end our lecture today? This is the last lecture on 3143 on the related to the syllabus. We will have another lecture next week. If you want to ask about the project, and remember also you can ask personally if you want. You can contact me to ask about the project, and remember that you have to present the project on the given date. It is mentioned the time in the assignment that given to you. Okay, any question? If not, thank you very much.